Hi, good morning everyone. My name is Romani Musa and these are my friends Jaden, Luke, and Campria. Our experiment for this lab is Balmer series on Rydberg constant. But first, let me remind you of lab number 4. In lab number 4 of Physics 2, we have done the experiment of understanding diffraction grading. In that experiment, if you remember, we did measure the spacing between the lines and we looked into the colors for the right and the left side. We measured the distances of the lines and then we calculated the wavelength for different light sources. We used mercury and helium test tubes. So, we are using this kind of knowledge and applying them into something even cooler, which is going to be the Balmer series of hydrogen. The three objectives of the lab are measuring the wavelength of the visible lines of hydrogen using diffraction grading, using the Balmer's formula to verify the results, calculating and comparing the Rydberg constant to the accepted values. So, as you learn in general chemistry, the electrons of the hydrogen can exist at specific levels of energy, and when these electrons are excited, they can go to a higher energy level, and they come down from a higher level to a lower one, and it will give off colors depending on the change of the energy. The formula Balmer series describes the wavelength of the electrons that are falling to the second energy level. The Balmer series is basically a set of lines we can see when the electrons drop to the second energy level, which is visible to our own eyes. We also have the Lyman series, which is a group of light lines made by hydrogen when its electrons fall from a higher energy level down to the first level. These lines are found in the ultraviolet part of the light, which we cannot see by our own eyes. So back to the Balmer series. The formula of the Balmer connects the wavelength to the Rydberg constant, and we know the Balmer goes to n equal to 2. Lambda is the wavelength, and r is the Rydberg constant, and n represents the principal quantum number of the higher energy level that an electron transitions when giving off a photon of light. So when n is 3, it gives off red color. When n is 4, it gives off blue green. And when n is 5, it gives off blue violet. And when n is 6, it gives off violet color. We'll also be using n times lambda equal to d times sine of theta to find the wavelength after we measured the angle. M stands for the diffraction order, and d is the grading spacing, and theta is the angle of light. This will help us to find the lambda and find the r value. So the purpose is connecting the theory to our actual measurements, and in this lab we will be using the hydrogen test tube and diffraction grading to find the hydrogen spectral lines, checking if the wavelength matches the Balmer's equation, and finding the Rydberg constant, and showing how the light colors are related to the electron energy change in the hydrogen.
Thank you, Romani, for that introduction. As you can see, these are the materials that we'll be using for this lab. It's the same materials as Lab 4, except instead of mercury, we are going to be using hydrogen. And for the example, we're going to be using helium in the actual presentation.
Now that you've seen the colors through the diffraction grading, we're going to take the distance between each of the colors that we see on either side and divide that distance by 2 to get the opposite side of our triangle. We're then going to measure the distance between our light source and the diffraction grading to get the side adjacent for our angle in the corner over here. We're then going to do inverse tangent of those two numbers of opposite over adjacent so that we can get our theta for the angle over here.
For the method section, we need to find the distance between the slits in the grating using the known lambda from when we used mercury. And then we need to measure the distance between the light and grating for the opposite. So we identify the colors on the meter stick, and we need to find the distance and divide by 2 so that we can find the opposite. And then we need to measure from the light source to the grating so that we can find the adjacent, and then arctan of that for theta. Then we can use theta to find lambda in our wavelength for the Balmer's equation, which Romani also explained. But we can use on the left side of the equal sign as our y-axis, and on the right side, excluding Rydberg's constant for our x-axis, so that we can compare the Rydberg's constant to the slope that we find in our results.
Here we have some explanations of the Balmer series and Rydberg's constant, which we covered previously in this presentation. So here we used a mercury tube to find the value of D. We found different color values using the hydrogen tube of red, blue green, blue violet, and violet. Solving for the sine of the angles from the distances that we measured, and then multiplying them by the slope we got from the Linus function using the mercury tube, then we get the calculated wavelengths for the new color lines, and then we compare them with the known wavelengths for those color values. Our calculated wavelengths were 630.306 nanometers for red, 489.028 nanometers for blue-green, 421.378 nanometers for blue-violet, and 404.464 nanometers for violet. We compared these to the known wavelengths, and we got percent errors of 3.958%, 0.5955%, 2.919%, and 1.392%, respectively.
So as you can see, we got a measured D value of 1026 from our mercury tube, which we have done before in one of the previous labs. We will take this value and use it to find the wavelengths of the colors that we see with the hydrogen tube. We took the distance between each of the colors we saw, divided by 2, then took the inverse tangent of the opposite over the adjacent, which gave us theta in degrees, which we then used in the equation lambda equals d times sine theta. Then we used 1 over lambda equals r times 1 over 2 squared minus 1 over n squared, where 1 over lambda was our y-axis and 1 over 2 squared minus 1 over n squared was our x-axis. So the slope would be r, or the Rydberg constant. Graphing this gave us a slope of 1.081 times 10 to the 7th, which compared to the Rydberg constant of 1.097 times 10 to the 7th gave us a percent error of 1.408%. Here you can more clearly see our graph using a linear trend line. We also took the known wavelengths of each of the color segments we saw from NINS, the National Institute of Standards and Technology, which gave wavelengths of 656, 486, 434, and 410. Compared to our calculated wavelengths using the D value from the mercury tube, we got wavelengths of 630, 489, 421, and 404. The percent errors were each pretty small, with around 4%, 0.6%, 3%, and 1.4%. You can see our calculations down below. In conclusion, we used the Balmer series equation to create a graph using 1 over lambda as our y-axis and 1 over 2 squared minus 1 over n squared as our x-axis, making r, or the Rydberg constant, our slope, getting an experimental value of 1.082 times 10 to the 7th. We achieved the experiment's objective of verifying Balmer's empirical formula of 1 over lambda equaling r times 1 over 2 squared minus 1 over n squared using Rydberg's constant of 1.097 times 10 to the 7th, ending with a 1.4% error.
So now I'm going to do the above and beyond section, but first I'd like you guys to listen to this video. Now that you've heard that video, it's clear that there's a peak of noise where it goes, no. That peak of noise is what we call a Doppler's effect, where when sound is moving with motion, it condenses the frequency and thus the wavelength also condenses. So as you can see, light has a blue shift and also a red shift. The blue shift wavelength gets shorter, higher frequency, and as we've seen, has the color of blue, which is closer in on our diffraction grating. And the red shift gets longer, has a shorter frequency, and has the color red. Well, sound uses the same shifts in an analogy. It's not really blue because you can't hear a color, but the pitch goes up and thus frequency increases when the car moves towards you, and thus we call that a blue shift. And a red shift analogy, pitch goes down, frequency decreases, and a car moves away. Astrologers use this to identify if a comet is coming towards your relative position or if it's going away from your relative position. Coming towards you, that's a blue shift. If it's going away, that's a red shift. Thank you for listening to our presentation.